So we know we can multiply a vector by a scalar. That's called scalar multiplication. Okay, can we do anything else? Can we add, subtract? Yep. And so we're going to look at addition, and so just a bit of language to help us get there. Whenever we add two vectors, the vector that we obtain as a result, the sum of two vectors, or in fact, we can talk about sum or adding a vector plus the opposite of the other one, that could be the difference too. But whatever we obtain after adding two vectors, that's called the resultant. Okay. Now that process geometrically is going to use what we call the parallelogram law. Okay. And you can read the description here, but I'll read it out loud for us. If we place two vectors so that they have the same initial point. Okay. So I'm going to start a picture. I'm going to make two vectors. Okay. Here is vector v, and here is vector, and I'll make w a little bit longer. Okay, place two vectors so that they have the same initial point and complete the vectors into a parallelogram. Okay, so what that means is so parallelogram has opposite sides that are parallel, right? So I would place a copy of v at the tip of w, and similarly I would place a copy of w at the tip of v. Okay, so this is creating the parallelogram. Okay, all right, so I completed that, and then it says then the sum of the vectors is the directed diagonal that starts at the same point of the vector. So it starts here and ends at their opposite. So this would be the vector that is v plus w. That's the resultant of v plus w. Okay, and so actually we get to see a bit of commutativity here too. Okay, commutativity, remember, is that you can, oops, let me do this first. Multitasking is not my forte. Okay, so commutativity means that you can do the operation in either order. Okay, so if we're ultimately interested in going from the beginning to the end, initial point to terminal point, right? We could do v and then w. Okay, so x plus y, or we could do w and then v. Ah, kind of cool. Okay, and so there we go. We know how to do the sum of vectors. Boom, done. Well, the story's a little bit more complicated than that. Oftentimes, we're not just adding two things, right? Well, we could extend the parallelogram law. And I mean, if you have multiple things that you're adding, you would just have to do it in sequence, right? So like, in theory, you could do that to that, or from here to there to go to the first point, and then, you know, you would make an arrow here, make an arrow here, and then you go the diagonal. Okay, fine. And then for the second one, you would say, okay, well, I'm already there. So, but if now I'm, you know, going to there. Oops, that's not what I wanted to do. Okay. But you'd have to do the parallelogram law many, many times with this diagram. Maybe a shortcut way to remember the sum of vectors is that the resultant that you get would extend from the tail of the first, or the initial point of the first vector, to the tip of the last vector. Okay, and so you get something like this. This would be the resultant. Okay, in this diagram. Okay, yeah. Sometimes, you know, with displacement or velocity, whenever you're working with a vector, you really don't care about everything that happens in between. You're just concerned with the beginning and the end. Okay, which is both a blessing and a sin, because maybe you do a lot of work in between and that doesn't get counted for anything, unfortunately. Okay, so that's a side note. Here we go. We have two vectors. We want to find each sum or difference geometrically. Okay. So I want to do v plus w. So I'm going to make a copy of v. Okay, I could, you know, copy it here, but I'm just going to freehand this. So I have v about like that. Okay, and then I'm going to place w with its same initial point. Okay, I'm going to use the parallelogram law. So here we go. Okay, I could also put them in sequence and just go tail to tip. Okay, if you want to do that, fine. Okay, I'm going to use the definition. So here we go. I'm going to complete the diagram here. Okay, so then the resultant v plus w extends from their common point, their common initial point, to where they both end up. Okay, so this would be v plus w. Okay, that's fine. V minus w, that's a harder question for us to answer. Okay, so mathematically, okay, we didn't learn about subtraction, but remember, subtraction is really just adding the opposite. Okay, and that's how we're going to complete this. Okay, so I'm going to say, okay, here is, I need to move this just a smidge. I'm going to do is off to the side here. Nope. So here is v. That's fine. Okay, now I'm going to say w would normally be here, right, and over here, but I'm working with negative w. Okay, negative w is going to be the same length, just in the opposite direction. Okay, so here's w, here's minus w, and I'm going to put that at the other side too and complete my parallelogram. Here's v, okay? And then my resultant is still going to start with that common initial point and go to where the vectors meet each other, okay? It's still a diagonal, okay? Just maybe different than the w plus v case. V minus w, okay? Something like that. So big takeaway, we can do subtraction just as well as addition, okay? And in fact, with both scalar multiplication and addition subtraction known, we get a bunch of properties, okay? Couple notes here, and I'll maybe zoom out so we can see the notes, okay? This one, this doesn't have arrows above it. It hurts me a little bit as a mathematician, but it's common for textbooks to, instead of writing the arrow over the top, which is, it takes more ink or something, I don't know, or it's very annoying to key in. Instead, it's very common to have a bold over it. So if you see like a very dark V, that's the same as saying V with a vector arrow over it. Okay. The other thing that you'll see in these properties is that there's a zero. Okay. That's called the zero vector. Okay. And it's a vector whose magnitude is 0, but vectors also need direction, but it's actually defined because it has no magnitude. It doesn't have a direction, okay? Or it has 0 magnitude, it has no direction. So just something to keep in mind, okay? Now, we're going to give you a very important example, okay? So we have vectors v and w have the following properties, okay? And we are going to have to work with the sum, okay? So I'm just going to make a quick little sketch. So length of v is 3, okay? I'm going to say v is here, there's v. We know its length is 3. Magnitude of v is 3, okay? And then we are working with w, okay? Length of w, magnitude of w is 5, okay? There we go. And we know they share the same initial point, okay? The angle between them, so this whole angle in here is 40 degrees, okay? So it says find the length of v plus w. Okay, well, we need to find v plus w first. I'm just going to make my little sketch. Okay, we know how to do the sum now. Okay, boom, boom. Okay, and then this would be v plus w. Okay, and it says find the length of that, and then also the acute angle that the angle makes with w. So to be clear, this up here would be a copy of w, and this would be a copy of v. So the angle it makes with it, it's kind of bad language, but we don't have any better ideas right now. So it's this angle here. So we want to know this angle theta for part B, okay? So we have a couple tasks ahead of us. How do we go about them? So here we go. We have to actually back up and do a little bit of geometry. Okay, I'll insert the resultant here in a moment, but I want to remove it for the time being. Okay, first we have to remember a little bit of geometry about parallelograms. Okay, if this angle down here is 40, that means that this angle up here in the opposite corner is also 40. Okay, so we have opposite angles are the same, and so that would actually carry through with the other angles as well. So if this is 40, that's 40. Okay, the sum of the interior angles in in a quadrilateral is 360, so that'd be 80 off of 360, which is 280. Okay, and that would be split between these two angles. So again, the math for these, so this is going to be 140. Okay, 140. Okay, and I got that by doing, so I did 360 minus 2 times 40, okay, which gave me the 280, and then divided that by 2. Okay, so use symmetry as much as you can. Okay, now I'm going to add that resultant back in. Okay, that's the v plus w. The reason I needed to do that analysis is because we're actually going to use the law of cosines here. Okay, if you take a look at the upper triangle here, or lower triangle, or whatever you want to do, okay, I'm going to separate this out. We have v, we have w, and we have the resultant, v plus w. Okay, we know this has length 3, this has length 5. We now know that the angle in between is 140, and since we're in that side angle side setup, that means we're going to do law of cosines. Okay, so I'm going to find the magnitude of v plus w, the length of that, right, via law of cosines. So solve that, set it equal to 3 squared plus 5 squared, so the other two sides squared, minus 2 times 3 times 5 times cosine of the included angle of 140 degrees. And when I do that, I get approximately, I should change this to approximately 56.98133. Okay, and then I have to square root that. Okay, so I'm square rooting that on my calculator, and so I get that the length of v plus w is approximately, let's say 7.5, go to 1 decimal place in this case. Okay, so I know the length, the resultant, and I was able to do it using the law of cosines. How neat. Isn't that fun? You're probably like, no, Professor Bright, no. Okay, but there we go. So now we've done that. Now our goal is to figure out for what part B is, what our answer to part B is. Okay, so B, it wants us to find this theta. Okay, how in the world do we do that? Well, we can do some more thinking. I have now in my triangle that this is, we know the length of the resultant is 7.5, right? Okay, now I think I know a side and angle pair. Oh, law of sines, right? So I'm looking for this angle theta right there, okay? So I'm going to use law of sines, and so I'm going to say, okay, sine of the angle that I want is opposite of the side length of 3, and that's equal to sine of 140 over 7.5-ish, okay? And so now I can say, okay, I can solve for sine theta. I would do 3 times sine of 140 on my calculator, divide that by 7.5, and I get, you know, this is approximately 0.2571-ish. And then if you do inverse sine of that, I get about, let's say 14.9 degrees. Okay. So does this make sense? Well, we need it to be less than 40 for sure. Okay, I mean, it's reasonable. All right, so there we go. So law of sines and law of cosines can come up when we're doing stuff with vectors. This video is a little bit long, but it introduced how do we do vector addition and actually subtraction via geometry, okay, using that parallelogram law. And then our last example linked together vector geometry and the law of cosines and law of sines that we've been using for a while now.